So we're going to actually go on to section 6 today, because I'm not going to ask you to take notes. I'm just going to ask you to pay attention so you don't have to hurt your brain too much writing stuff down. No. So these are some additional topics that are in the geometry section. I don't have any homework assignment out of it, so I'm just trying to give you an overview of what the usefulness of these things are. So section 4 and 5, as you know, we did formulas for area and volume and perimeter, which if you watch the review, you found out that I'm not actually testing you on that this time, but I will test you on that next time. So section 6 talks about transformational geometry. If you've ever taken pre-calculus, you've done some transformations where you had to what's called translate and rotate and reflect. And also adjust the size of the image. So it's basically taking an image and transforming it to a different location, a different orientation, a different size, and how do you do those kinds of transformations. So, you know, you think about if you're an artist and you were looking at your model and you might be transforming it in terms of the size that the actual person is to putting it on your canvas. If you were, I mean, a camera does it automatically. It transforms the image to a smaller scale size image. But sometimes even say if you're designing something, you're an artist or a designer, industrial designer. So does anybody know what an industrial designer does? As the name implies. Yeah, okay. So if you look at, let's say, Target, you know, they have a designer that designs nice-looking tea kettles or functional things that are functional, but they look good as well, like iPhones. You know, the people who design the iPhones, they're not just designing it for working, but they also want to make it look good. And so an industrial designer is kind of like an architect, but they design industrial items instead of buildings. My son-in-law, he got a degree in architecture with a minor in industrial design. So those chairs that we looked at the other day, that would be somebody, an industrial designer might design the chairs. And part of that is just taking an idea and then synthesizing something, which might involve these kinds of transformations. So one thing is reflecting an image across some line. So in the simplest case, what you have here is you have a line M, and you have an object, which is a triangle, and you want to reflect it across this line here. So everything is equally spaced across the line and also at right angles to the line. So if we wanted to look at the original image and the reflected image, one thing is we would draw a line from point A to line M, and it's at a 90-degree angle, and then you would make point A prime the same distance on this side of the line as it is on the other side of the line. So I draw this line, and then I measure the distance from the line to this point, and then I take that distance and measure it. Likewise, the same thing for point B. You would draw a line from point B perpendicular to line M. You would measure the distance from the line of reflection to here, and then you would measure the same distance down there. And finally, you could do that with C. And what you end up with is an image that's just transformed. It's basically a similar triangle. In this case, it's actually a congruent triangle because all of the angles and all of the lengths are the same. They're just on the opposite side of the line. Now, the lines don't have to be horizontal. Well, here's an example. Just it's a picture of somewhere, and if you look at the reflection in the water, you know, the reflection is going to be symmetric around the water line. So wherever the water line is here, and you see the building, it's the same size and everything's upside down, but it's transformed, it's reflected. Anybody have any idea where this may be? Europe something. What's that? It's near a body of water, yeah. So it's probably not Czechoslovakia or Czech Republic or Hungary. Yeah, it is in Europe. I'm not exact 100% sure. My guess is Norway. Okay, that's kind of the typical architecture that you would see on the coast of Norway. And I know that because I've seen pictures. My mother went on a cruise one time, and they went into all these little coastal areas, and they look kind of like that. So anyway, that's an example of a reflection in a real situation. Now, you can also have a reflection across a line that's not just horizontal. So if you have this triangle and you want to find a reflection of this triangle relative to this line, again, you would draw lines from our points that are perpendicular to the line of reflection. You'd measure this distance, and then you'd use that distance to go the same value on the other side of the line. And as a consequence, you could find these 3 points that are associated with the reflection, and you could just draw lines. You could draw a line between point here, this point and this point, which would match every point. So you don't have to define every point on the line. You just have to define 2 points in terms of the reflection. So to make the reflection of this object, I only need 3 points that I can measure and plot, and then I can draw lines, straight lines between the points to get the actual reflection. So there's an example of something that will probably require more points, but every point on this object has a corresponding point on this object that is the same distance from a line drawn perpendicular from the point on one object to the line of reflection. And there's another one. In this case, you've actually got a point that's in both. There's a special name for it, and I can't remember what it is. It's on the next page somewhere. It's called an invariant point. There we go. So this point is invariant because it's on the line. It's on the line of reflection. So it's on both images. So this is invariant, meaning it doesn't move. These are away from the line of reflection, and so they are not invariant because they change. Okay, and what this basically is saying is that if you have a reflection, if you have a line in the original drawing, then you'll have a line in the reflection, and all the points on that line will remain in a line. So you only need the 2 points to draw accurately to draw the reflected image, because all the points between A and B are going to remain collinear, which means that they are going to be all in the same lines. So it just makes drawing reflections pretty easy once you define a few points. Okay, so that's one thing, reflection. Another thing is that if you draw a line that's within the body, so instead of drawing the line outside of this, so if I'm looking for the line that's the reflection of line AB, which is A prime, B prime, notice that this line of reflection doesn't intersect this line that I'm trying to reflect. Whereas if I take this triangle and I draw it appropriately, so one part of the line goes through the vertex and the other part of the line goes through the midpoint of the opposite side, what I have is a symmetrical situation. Meaning that for this triangle, if I go equal distances away from the line of symmetry, I get a point. So if I start here, this is my line of symmetry, and I go this distance left, if I go the same distance right, I'll get the corresponding same, I'll be on the image. If I go, say I go from here to here, that distance, it says if I go the opposite direction, the same distance, that I'll also still remain on the image. Now I could draw a line of symmetry between any of the vertices and the corresponding midpoint of the opposite side, then I could have a symmetry. So a triangle, in this case it's an equilateral triangle, it's going to be, have three lines of symmetry. In this case we have the line of symmetry, and we see that, going either side the same distance perpendicular, we are on a similar kind of portion of the figure. So there's a lot of things that have symmetry. This is a case of a snowflake. If I took a line anywhere, well, not anywhere, but appropriately drawn, like for example right along here, I would see that if I go perpendicular to this line of symmetry at a certain distance, I should see a corresponding similar part of the geometry on the other side of the line of symmetry. And there's lots of lines of symmetry here. I could either draw them along these snowflakes or I could draw them exactly in between, but it just means that the figures have some regularity to them. So there's your, I guess that's a piece of ochre. And again, it has symmetry. If I were to draw a line from here right through there, it's kind of like a star. Again, if I go this far, I have this element of the drawing, and if I go this far, same distance, I have a similar kind of part of the object. This would be an invariant point because the part of the figure is on the line of symmetry. So vegetables, flowers, a lot of things in nature have symmetry to them. We have symmetry to a certain extent. Our internal organs aren't symmetric, but our external body is reasonably symmetric. All right. Oh, I'm not sure. Yeah. I mean, looking at the heart itself, it's off center, but it is fairly symmetric. They're not all symmetric, but there's a leaf. And then in architecture, you see symmetry all the time. That's the inside of a medieval cathedral. That's the ceiling. This one actually is one of those things that, one of those, what do they call? Yeah, is that what it is? Yeah. Okay. So I just put that in there. Okay, so that's what symmetry is. Symmetry is you can draw a line somewhere on the object, and on either side of the line of symmetry you see the same distance from the line of symmetry. Either way, you see the same kind of portion of the original image. Now, translation, really, it's just moving something but keeping its orientation the same. So notice I'm not rotating this thing. I'm keeping it pointing vertically. Or I can move it this way. That would be translation. This is translation. Even going diagonally would be translation, as long as I keep this dimension of the remote pointing upward. It turns out that you can think of translation as two reflections across two parallel lines. So let me try to demonstrate this. So here's one line of reflection. So what if I reflected it? What would happen is I'd put it equally on this side like that. Okay, so that's one. And then what I do is I have a second parallel line, and then I translate that. I mean, I rotate it. And really, I should be rotating it this way. So if I think about rotating this thing around this line, I'm actually doing that, and then I do it again, and it comes back to the front and to be more perfect. Because otherwise, it didn't look. Why did I have to do it again? But it's really I'm reflecting that like that, and then I'm taking it like that, and it comes back to its original orientation. In 2 dimensions, what you do is you take the original object, you reflect it around this line M, so that these distances are equally far from the line of symmetry. But you can see that this point is now all the way over there, so that's why you have to reflect it again. If you reflect around this line, this point becomes that point, and that point becomes that point, and now you can see that they're in the same orientations, so that this one is pointing to the left. And that's why you have to reflect 2 times to get a translation. And again, you don't have to do it. The only thing is the 2 lines have to be parallel. So if I want to translate this object from here to here, again, I'm keeping the long side pointing upwards. When I reflect it across this line, which is now at a 45-degree angle, this line maps, this point maps to that point, this point maps to that point, this point maps to that point, and this point maps to that point. So then I have another parallel line, so M and N are parallel, so I reflect again across this line. So this line maps, this point maps to this point maps to that point, this point maps to that point, and this one goes there. And now you can see that they are in the same orientation as they were originally, but they have just been shifted. So in pre-calculus, when we talk about translation, we talk about shifting, shift left, shift right, shift up. So that's all translation is. And what they're doing is just defining it in terms of reflections instead of just move it to the left and move it to the right or up or down. It's just a different way of talking about translating something. So that's translation. Must be getting close to 1 minute and 17 seconds. If you want to rotate something, so what we're talking about here is rotation. If I rotate it around this point, that's what it's going to look like. So this point remains fixed where my finger is. I'm just moving everything around that point. That's rotation, which you understand. Again, it's kind of interesting to think of it in terms of 2 reflections. And instead of reflecting across 2 parallel lines, you reflect across 2 non-parallel lines. And the angle that the 2 lines make with each other, this angle right here, is the angle that the object is rotated through. So there's no angle. So there is no angle that we rotated through. But what we do here is we take this point and reflect it across the m-axis to here. We take this point, reflect it across the m-axis to there, and we take this point and reflect it across the m-axis to there. So these are reflections of each other. Now we have the second axis, which is at an angle, and we reflect across this line. So this point goes to there, this point goes to there, this point goes to there, and you draw it, and it looks like the original figure, but it has been rotated around this point of the 2 lines where the 2 lines intersect. So this is our center of rotation, and it's just moved. All these points here are the same distance from the center of rotation. So the distance from here to here is the same as the distance to there to there. The distance from there to there is the same as the distance from there to there. So that's what rotation is. But again, I never, until I taught this class, I never thought of it as 2 reflections across non-parallel axes. So it was a new way of thinking about it. Okay, so we're getting ready. So let's everybody 2 people apart.